Hello and welcome to our presentation about how to build digital load cells with PICOSTRAIN conveniently. My name is Ralf Emberger and I will guide you through this presentation today. First of all, let me say some words about acam. acam is a fabless vendor of integrated circuits in the field of electronic measuring equipment. We currently have 4 product lines for various type of sensors, all based on time-to-digital converters, so-called TDCs, as a measurement core. We are based in the headquarters in the southern part of Germany, close to Karlsruhe, and we were founded in 1996. We have distributors all over the world, where Secom Telecom is our Chinese distributor located in Shenzhen with many local offices all over China. The PICOSTRAIN product line provides innovative electronics for strain gauge sensors with very high precision and low current consumption. It was introduced in 2002 and we are now in the 4th generation with our latest product PS081, which is a single chip solution consisting of a microcontroller, converter and LCD driver. On this slide you see some PICOSTRAIN milestones. 2002 we introduced the first generation of PICOSTRAIN with PS01. In 2004 we won the Innovations Award for PS02 at the ISWM, an American weighing technology trade show. And in 2007 we introduced PS08 as a single chip solution, where we now have the enhanced version of that with PS081, which was introduced in 2009. Typical applications of the PICOSTRAIN technology are solar scales such as solar body, solar kitchen or solar hanging scales, generally low power scales, but also high resolution industrial scales, as well as calibrated scales, for example OML or NTAP approved scales. Of course, digital load cells, where we want to focus on today, and also wireless load cells. Other fields of applications where strain gauge are used but not directly related to weighing technology are medical or white goods, force and temperature. So let's have a look how the current situation is. The digital load cell was in the last decades a niche product compared with its counterpart, the analog load cell, which is still state of the art today. The quantities are fairly low. This is mainly because the production and the adjustment which needs to be done manually is elaborate and expensive. However, they are used in some areas, for example where long cables are used and a loss in signal strength is not tolerable, or where you run various load cells with one single microprocessor, where EMI is important and where you have problems with electromagnetically noisy environments, where fast replacements of calibrated cells is important, so where you replace the whole cell which is intrinsically calibrated. So this applies, for example, for truck scales or generally in electromagnetically noisy environments. However, the analog load cell is produced in much higher quantities compared with the digital load cell, and this is due to the expensive production of the digital load cell. So today's main challenges in making a digital load cell are mainly the production. The production is elaborate and costly. This is mainly because the mounting and assembling and the temperature adjustment cannot be combined in a convenient way. So this means it has to be done separately, and the load cell calibration is taking a large part of that. It's very elaborate and needs a lot of time. You need a lot of efforts for compensating for gain and offset drift. So having specifications like OML 6000 is quite a hard job to meet the specification, and it's not easier than adjusting an analog load cell. Of course, a lot of manual trimming of the load cell's adjustment resistors need to be done, and so automation is hardly not possible. So how does PICOSTRAIN make the production easier today? Well, thanks to the convenient temperature compensation, we can simplify the whole workflow. So how does this work? The integrated microcontroller has a temperature compensation which is done without adjustment resistors. So you can compensate for gain and offset drift very comfortably without a mechanical trimming of adjustment resistors. This leads in the mounting and assembling procedure to a very simple two-step approach. First, you mount the complete load cell with the electronics without any mechanical trimming or adjustment by hand, and then take the whole cell and go to the temperature drift chamber and make the gain and offset adjustment just by the method of the integrated microcontroller. So the whole workflow is simplified and the results in regards of quality are very good. So if we compare the workflow which is done today with the possible one to be done tomorrow, we can see that today the calibration of the load cell is elaborate. You have to do that first, and afterwards the electronics is mounted. So it's always two steps where automation is hardly possible. With the PICOSTRAIN approach, you can first mount the whole cell together with the electronics, and then there's adjustment for temperature done, but without mechanical trimming. So the adjustment is basically done by the integrated microprocessor, and this can be fully automated, of course. With this slide, I want to introduce you to the PICOSTRAIN temperature compensation. I don't want to go too much into the detail, but just give you a roughly idea. Basically, what we do at PICOSTRAIN is charging a capacitor, here labeled with C load, which is then discharged over a half bridge, over the strain gauge resistors of the half bridge, and then afterwards over the other half bridge. So having a plus and a minus extension with the strain gauge resistors, you get as a result some discharging cycles which look like here in this picture, where one time interval is longer than the other. The ratio of this discharging times equals to the ratio of the resistors. As our TDCs, the time to digital converter, have a very high resolution in the range of picoseconds, we can generally achieve a very high resolution when using it for weighing scales. More than that, when it comes to temperature compensation, we can determine the size of our span. So you can see that our span is here in the path of the one half bridge, but not in the path of the other one. So drawn in another manner, this would correspond to this picture. So you can easily imagine that we can determine the size of our span, or let's say the time interval needed for passing our span, we can determine in the chip and also correct it that way. So mathematically expressed, you have here the equation which is the ratio of the strain gauge resistors, but with the two correction factors TK gain and TK offset. So the offset is for correcting the zero offset, and the TK gain is adjusting the R span by means of a register setting. So this is how it basically works, and it is described in a very detailed manner in a dedicated white paper. So let's have a look now what the advantages are by building a digital load cell with PICOSTRAIN technology. The number one advantage is that the production gets simpler and that you save cost. This is thanks to the more efficient workflow as described earlier, which leads to higher throughput times and that you can speed up the whole production. And at the same time, you can reduce costs. For example, there are less labor costs because manual adjustment is not needed anymore. You can do that automated and therefore save labor costs. Also, there's a reduced number of components, so that means the bill of material gets shorter, and the PCB size itself is very small. So there's a high integration and a reduced number of components. This all together leads to increase in quality and reliability without additional expenses. That means the efforts you are investing, for example, for an OIML 3000 scale will give you a quality good for OIML 6000 scale. The second main advantage is the convenient temperature compensation of PICOSTRAIN. As already mentioned, you are able to mount the whole unit, that means putting the electronics into the load cell and then calibrate it together. So this leads to our two-step approach in assembling and mounting, where you first mount the whole cell together and then make second the compensation by the PICOSTRAIN method. So this will speed up your production, you have faster throughput times, and there are normally no iterations in adjustment procedure necessary. Of course, there's also a higher degree of automation possible with this workflow, and the quality, as mentioned, gets better or higher. So one advantage also is that the DLC itself, which is conformed then to legal specifications like OML, can be easily replaced in the field that way, as they are intrinsically calibrated. Another advantage, which automatically comes with the PICOSTRAIN technology, is the low current consumption. A low current consumption may be required for battery-driven or wireless DLCs or portable DLCs. The PICOSTRAIN measurement principle is a pulsed one, so that means there's no steady current in the bridge and current is only consumed when the measurement is active. This leads to very low current consumption in general. For example, if you want to realize 3000 OML divisions, we can do that with 180 microamps. As a consequence of that, the self-heating is also significantly reduced. So you won't see a zero drift in the first minutes when switching on the scale. A further advantage is the use of DLCs in standard scales. This may not be so common nowadays, but we think the basic idea is very convenient. The basic idea is to split up the scale in an analog part and a digital part, where the analog part has the load cell with the electronics for all what is needed for weighing, and there's a digital part where you have only your digital board interfacing the outside world, buttons or LCD, for example. The advantages of this approach is that you can design your PCBs more effectively to their purpose, analog or digital. You can reuse the PCBs in various type of standard scales, and of course the development work can be divided, so you can have a group for digital design and the other one for analog design. Of course, what comes with that approach automatically is that EMI behavior gets better, because it's a very encapsulated way to build the load cell, and you already get here a digital signal out, so the EMI behavior will be better. So summing up the advantages, we can say that building a digital load cell with PICOSTRAIN technology has several technical and commercial advantages. You can produce a high quality load cell with less efforts and costs than compared with nowadays production of digital load cells. So let's come now to the practical aspects of the presentation. When we talk about the DLC prototypes ACAM built up in the first quarter of 2010. The goal was to investigate if a setup like we imagine it was feasible, and how the results would be in regards of resolution, temperature, behavior and current consumption. Therefore, we asked our load cell manufacturer to give us a standard T3 load cell, but not wired and no silicon glue on top, but only the naked load cell body as seen here in this picture, with the strain gauges applied and 1 hour span and a milled out area for putting in the PCB. In a second step, we then designed a small PCB with a dimension of 22 × 19 mm to put it in the milled out area of the load cell body. Then we connected the strain gauges according to the PICOSTRAIN connection, which is shown here again, 2 half bridges connected to a full bridge with 1 hour span in the path of the 1 half bridge. So here you can see the red wires to make the connection to the PCB. So this is basically what you need for connecting. Please note again that there are no additional adjustment resistors needed to do the temperature compensation. This is later done by having the 1 hour span and the temperature compensation inside the PS081. Of course, in the end, there's put a silicon glue on top. We made one transparent type to demonstrate the wiring, which can be seen on our booth, and several non-transparent types to avoid the influence of the ambient light. Of course, we run then several tests with these prototypes, for example noise investigations, temperature drift tests and also the current consumption. So in the next slides I will show you the results of some of the first prototypes. So first of all, we did some noise figure and stabilization time investigations. The result is shown here in this noise diagram, where you can see 2 red dotted lines showing 1 division out of 200,000 stable divisions, and the blue curve is the noise figure we recorded. So we were almost at 200,000 stable divisions, or internally almost 1 million effective divisions. Let's say 150k stable divisions are good feasible. And to give you a feeling what that means, for an OML 3000 scale, you need approximately 15,000 stable divisions. So what you see here is factors 10 better than what you need for an OML 3000 scale. And this is on the basis of a standard C3 load cell with 350 ohms and a supply voltage of 3.6 volts. Generally, the resolution and stabilization time is a matter of configuration in PICOSTRAIN. Here the stabilization time was 0.7 seconds. So overall, the resolution is very high and much more than you need for OML 3000 or 6000. In a second step, we then investigated the temperature behavior of the cell. So first we adjusted the load cell according to the PICOSTRAIN temperature compensation. That means we determined the proper factor for gain and offset drift and put them into the registers of PS081. What you see then here in this diagram is the result of determining the gain drift, the remaining gain drift of the DLC prototype, where the red lines are the OML 6000 limits for the gain drift, and we recorded here the gain drift at -5, 10, 25 and 40 degrees Celsius. And you see that the gain drift is very nice within those limits, so the gain drift would be good for making a scale according to OML 6000. We then also recorded the zero drift of the prototype. This time we show you in the diagram the before and after curves. So that means again the red lines are indicating the OML 6000 limits, where the orange curve now is the zero drift before the adjustment with the PICOSTRAIN compensation method, and the blue curve is the line after adjustment. So you see that the offset drift was almost 35 divisions before and in a very low range after the adjustment. Please note also that the gray dotted lines are temperature jumps, for example here from plus 40 degrees to minus 10 degrees, and OML defines a settling time of 2 hours, so that means the real offset drift, which matters to the OML specifications, need to be looked up here in comparison with here. So the dynamic drift, which can be seen right after the jump, is not important for the OML specification. Generally, we can say that this offset drift is a very good offset drift and would be good for making a scale according to OML 10,000. Well, after showing you the very nice temperature drift results with the PICOSTRAIN temperature compensation, I now want to show you the current consumption, which we measured also with the DLC prototype. Again, current flows only when the measurement is done according to the pulse measurement principle of PICOSTRAIN. There's no static current in the bridge, which leads to very low currents generally. In this table you can see in the first column the peak-to-peak stable divisions, in the second column the stabilization time, and in the third column the current consumption. And here you can see some remarks what the resolution is good for. For example, the second line and the third line, they are good for OML 3000 and 6000 divisions, and you need a current to realize that resolution of 200 microamps or 650 microamps for OML 6000. So it's a very low current consumption generally if you compare that to a classical AD converter solution, where you need even some milliamps, up to some milliamps for the converter itself. This here our current consumption for the whole system, including the strain gauges. At last I want to say some words about the interface, which is a SPI or SPI bus. This is a full duplex serial interface bus for wire-based, and is a standard protocol in master-slave applications where up to 3 meters are no problem to connect. So it's perfectly suited, for example, within standard scales, as there's a very easy interconnection between the DLC and its counterpart, for example a microcontroller. If you want to realize other protocols such as RS-232 or others, there are external transceiver chips available. So in summary, we can say that building up the DLC prototypes was successful, and we could show that the new workflow like we imagined it was possible. We obtained very good first results in the area of noise behavior, temperature adjustment, and the low current consumption. We described everything step by step, how it was done and how the results were, in a dedicated white paper which will be available on our booth. So this was the last slide of our presentation, and I want to thank you for your attention and your time. Please visit us on our booth on B11, B12, B23 and B24 and get your free DLC white paper copy. We're looking forward to assist you and to help you with any questions you may have. Thank you again.